Alright, let's quickly talk about sequence spaces. These are types of spaces. So we have the sequence spaces are the ones whose elements are expressed as infinite sequences. So each element of this space are expressed as infinite sequences, right? So now the first one is the LP space, all right? So if we want to show that a sequence is the type LP, so each element will be a sequence, that is, X will be expressed this way as a sequence, then each element of the sequence will be a complex number. Remember that natural number is a subset of the integer, which is a subset of the rational numbers, is a subset of rational number of real, which is a subset of complex. So all of these are also complex numbers. All right, so now it must also satisfy this, that is remember LP. So the pth power of the absolute value of each element, when you sum them from 1 to infinity, must be finite. That is, must be less than positive infinity. It must be finite. So then you will say that it satisfies LP sequence space, or is an LP sequence space. All right, let us solve an example. Alright, this is an example. We are to show that the point X is in L1, but Y is not. So we have P to be 1. So we have our P to be 1. Remember, the first thing you have to show that each element, or it must satisfy this 3, must be complex. So remember, 1, -1, 1, 0, they are all complex numbers, just like I mentioned earlier. So each of these are in complex, then it must be a series, right? So it must be I equals 1 to infinity. Okay, so and X is definitely expressed that way, right? X is expressed that way, which is what I equals 1 to infinity. So we have x1 to be 1, we have x2 to be -1, we have x3 to be 1, x4 to infinity to be what? To be 0. So yeah, so we have x that way. Then the third one, right, says that what? For each one, you find the sum x1 raised to the power 1, our p is 1, plus x2 1, plus x3 1, plus x4 1, plus is what? Is finite. All right, so we know x1 to be 1, 1 raised to the power 1 is 1, -1 raised to the power 1 is -1, x3 is 1, x4 is 0, x5 is 0, so we have 0 plus 0 plus 0, and this is what? This is 1. This is 1, and this is actually finite. It is less than infinity. So yeah, we have that X is actually in L1. All right, so let's check for Y. So for Y, we see that each element is actually in complex. 1 is a complex number. It's the real part. All right, so we can see that Y is also expressed this way, right? I equals 1 to infinity. So we have that y1 is 1, or is y2, is y3, is like that, right? Is 1 to infinity. All right, so the third one, which is sum to infinity, yi1, right? Which is still yi. This is what? 1 plus 1 plus 1, right? To infinity. So that shows we sum 1 to infinity. So this goes to infinity. This cannot be less than infinity because we continue to sum 1 to infinity. Because we have 1, 1, 1, 1, 1, 1, 1 to infinity. So this cannot be finite. So we sum 1 to infinity, that is. Remember, if you have something like this, or let me tell you something, when you have this, then with the constant, let's say 2, this is same thing as n times 2. That is, you are summing 2, like n numbers of 2. So you have 2 plus 2 plus 2 plus 2 plus 2 plus 2 n times. So that is n times 2. So the same way, this is infinity times. So which will be infinity times 1, which is infinity. You can think of it that way. So it cannot be finite. So this implies that y is not in L1. So we have that. Alright, so the second one will be L infinity. This is just like infinity norm, right? Infinity norm. And this is what? 1 norm, right? So 1 norm, just like we did. 1 norm is just, right? Just like what I've done, right? So if it is 2 norm, then you have 2 here, right? Then you can have n here, whatever. All right, so this is infinity norm. Infinity norm is just like taking maximum of xi when I ranges from this, right? But now we have infinity here, right? We have infinity here in this our case. All right, so maximum, it's just like boundedness, right? So when we are talking about L infinity or infinity norm, so if x is set of all bounded sequences, then when do we say so let's say x contains like some sequences, this. So when do we say each of these sequences is bounded, right? So there exists a constant, okay, greater than 0, such that the absolute value of that constant is what is less or equal to m. The absolute value, right? The absolute value of the sequence is less or equal to the constant. So this is boundedness. So you should remember the definition. So that is boundedness. So this is what the sequence space L infinity is all about. So if you have x in L infinity, remember x is complex, such that what xi's are what less or equal to some constant mx. So m can sometimes may depend on x. So we have for all I equals 1 to infinity, as we said in our case. So remember, m is a real number, right? M is greater than 0. M is a real number which may depend on x. So this is just the definition for L infinity. If there is any problem as we move forward in the course under this, then will let us know. So let's move to another example.